Okay, so today we have Felix Hill here from Cambridge University. He will talk about neural language generation models. He's interested not only in the nitty-gritty details of neural language models, but also in how you train them in end-to-end systems so that interesting properties emerge from the application itself rather than building it up in an purely engineering way. So without further ado, I'll let him talk about these things.
Okay, thanks very much, Novosha, for inviting me. It's great to be here. Thanks for coming. So I guess a lot of you know already, but language understanding is really hard, right? So here's a highly realistic example from a kind of top-of-the-range personal assistant, which shall remain anonymous. But it was asked, I think I have alcohol poisoning, what do I do? And the response of the system was, I found 7 liquor stores fairly close to you. So you can see that here the system hasn't understood the language in a way that we would find satisfactory. And in fact, I think almost any speaker of English would be able to give a more useful response to that, regardless of really what they know. So there's a long way to go. And language understanding for me is hard for 2 reasons. So one reason is that it's just hard. We try to simulate language understanding and linguistic behavior in machines, and that's hard. It's also one thing that maybe makes it hard is that we don't really know how humans solve these problems with the information that they have available from the moment they're born, and also when they receive some information in order to try a particular task. So the way I've tried to address this problem in my research so far is kind of as one of joint optimization. So a little bit of following progress on how we explain human language learning and maybe contributing to it in a little bit using the resources that I have available. And also to try and improve models of computational language learning and understanding. And then in the long term, I'd like to try and incrementally improve performance in both of these things. And I think that that's a good way of coming to a good level of overall performance on both tasks. And it may well even be impossible to resolve one of these questions without resolving the other. So the way I've attacked the problem so far in my graduate studies has been with deep learning or neural networks. So I haven't done that because they're particularly new or original. This guy was making his networks deep in like the 60s. And it's not because they're particularly fashionable at the moment either, although they are. So it's kind of hard to convince people of that, because when you say that, they just say, oh yeah, you would have done whatever was fashionable at the time. But in actual fact, there's another thing. It's not because they're a perfect model of the human brain, right? So I'm aware that an artificial neural network is not like a brain in anything other than a very crude, high-level sense. But one of the reasons that is very compelling for me as someone who's interested in language and cognition is this, right? So neural networks generally form distributed representations of their input. So in a raw stream of linguistic data, a neural network will represent concepts in the input as a series of activations over a finite number of units. And these activations can be real valued. And each of the individual features doesn't necessarily correspond to something that we would particularly understand in the wider world. This contrasts with a localist or symbolic view of processing, in which we allocate a unit or something, a variable in the model, to correspond to some particular discrete thing that we know in the world, and then those features are mutually exclusive at the input level. So yeah, for me, the kind of overriding essential property of a neural language model is that it computes distributed representations of its input, of the raw linguistic input stream. It also learns a parameterized function to compose or do something with that input or those inputs, in order to reach some representation which is then optimal in some way for doing something with language that we want to do. And that thing can be making a prediction, making a decision, generating some output, whatever we might need from our language technology. And
you consider the effect of the decision on the input.
Right, exactly, yeah.
So there's a lot of that.
Exactly. So these These are kind of both parameterized aspects of the models. One of them is the composition function. The other is the representation of the input. And they're optimized jointly through the same process of backpropagation and gradient descent. And for me, that's one of the essential properties of neural language models. So what's so good about these distributed representations? Well, if we use distributed representations, we get a number of aspects of human semantic cognition for free. So we obviously get automatic generalization, which is thanks to shared properties, right, which is quite nice. So if we knew, for example, that this image represented a dangerous thing, then we might have some sense, without doing any real clever inference, that this image represents something which is also probably dangerous because of the shared property of stripes. It's also well known in human cognition that many aspects of cognition and conceptual processing are kind of gradual. So this concept here, we're all quite happy to understand that that would be pretty prototypical for a bed. This thing here we would understand as probably being further away from our core notion of bed. And this can be shown empirically by behavioral studies on humans. And when we represent input in a continuous vector space, we get various ways of naturally computing these gradual or soft semantic effects that we maybe don't get automatically from a symbolic model. But finally, and when thinking about language, perhaps this is the most compelling argument, I think with distributed representations, we've been able to get one of the most clear examples of successful unsupervised learning that maybe exists in the whole of machine learning, but certainly in language, right? So that's the notion of distributed word representations. It turns out that the way words are arranged in text means that we can define algorithms for inferring general purpose word representations, which are actually useful for a range of different things we might want to do with language, right? So these word representations, which are sometimes called word embeddings, they're obviously very well discussed in the literature. They're useful in the classical sense of unsupervised learning, in that we can train them on a body of text without having a real sense of what we want to use them for. And then we can, maybe with a little bit of, so in this work, for example, they used a little bit of training data, a little bit of labeled data to then optimize performance on a range of different linguistic tasks. And of course, they showed that having these as input features for the input gave better performance than just having other features that might have been hand-coded. It's also the case that these word representation spaces align naturally with certain aspects of how humans understand word meanings, right? So they match, the similarity in these spaces often matches how similarity is intuited in human semantic processing. So these word representations have been very successful. And that's kind of the starting point from when I started to look into this world and see how I can contribute to language understanding. So there's a few stages of this talk. It's not going to be none of these is going to be particularly long. The first one, I'll discuss ways in which I've tried to scale up the benefits of distributed word representations to larger linguistic chunks, such as phrases. The second one, I'll then talk about how when we're trying to understand what language means, it's also useful to understand a wider context, which can be the discussion that was happening previous to that, or something else which was in the document, and how this is not easy for neural language models to take into account, but I've developed some ways of doing that. Then there's a small section on ways in which we can use neural language models to learn a little bit about human cognition. This is kind of the other side of the equation where we try and optimize for understanding human language processing a little bit better. And then I'll talk about some limitations of all of this work and how a proposal for what we can do in order to tackle some of those. So one question that I tried to address in my work is, can we learn general purpose representations of phrases, much as we have done quite successfully for words? And the way I went about this was by exploiting dictionaries. So dictionaries are useful in terms of linguistic resources because they generally exist. And in particular, there's many dictionaries in English, but there's dictionaries in many of the world's languages. So the recipe for this work was a dictionary, or several dictionaries, and a pre-trained word embedding space. So this is just a really good quality space of words trained on many billions of words of text, such that this space is known to correspond to how humans understand the meaning of words. So lion and tiger and other things which we think of as being close together are close together in this space. So what did we do with the dictionary? Well, dictionary, of course, defines correspondences between single words and phrases, those phrases being the definitions. So we can basically just consider this to be the problem of learning a mapping, and then insert neural language models to learn this mapping. Of course, we can also take things that are a bit like dictionaries, but not exactly dictionaries. So that would include, for example, encyclopedias. Encyclopedias are nice because they have maybe more factual knowledge about exactly, general knowledge facts about named entities, whereas dictionaries might focus more on common words. So we can get something like a definition from an encyclopedia just by taking the first sentence of any article. So that generally summarizes in a high-level sense what the concept is. And provided that the concept itself has a single word for a name, then there's no problem finding it in our pre-trained word embedding space. So we can put in a model here to learn the mapping between the pre-trained word embedding and this phrasal linguistic inputs. So in this model, these features don't update. They're just, you can consider them as a target, a fixed target. So this is kind of like a regression problem where we're trying to map into a continuous valued space. An obvious model to put in here is a recurrent neural network because the length of the phrase here is not fixed. So this RNN doesn't have any issues with reading phrases of different lengths. So we did that. Of course, there's a simpler model that we can do, which is to take out the recurrence. So here, the transition matrix in this model, which we called the bag of words model, is just addition. So in this model, it's invariant to changes in the word order of the definition. So whatever in whatever order it reads, the input, it will arrive at the same point in the embedding space.
The difficulty of this is that you don't have, there's no place where you put attention there, right? It's known that doing this kind of thought vector approach that we have shown here, when the sentence gets long, then the quality becomes worse.
Right, yeah. There's no attention in this model.
There is, attention, but you need to have end-to-end tasks to do that. In your case, you don't have that.
That's true.
It
wouldn't be trivial to think of a way in which we could encode it, have an attention-based approach to this model. But one thing that I would say is in the current case, word definitions are generally short phrases. Yeah. So some of the evidence, which I'll talk about in a minute, demonstrates that maybe attention wouldn't help in this case. But okay, and then there's another variant we tried. In this model, the input is represented by representations trained in the same space as the target, right? And actually, when we train these representations are not updated; they're fixed. So all we're learning is what's in red. So we're learning parameters which map that representation space into a different one. There's a nonlinearity here, and then they feed into the hidden layer of the recurrent neural net, which is then updated and reads as normal. And there's also an addition version of this variant, right? So we can just have addition here as well. So there's 4 variants of this model. So what's the point of doing this? Well, other than general purpose phrase representation learning, there's a few obvious sort of immediate applications. So one of them is the somewhat quirky application of reverse dictionary, right? So this is an application that maybe is useful for writers if they can think of how to describe a word they're looking for, but they can't think of the word itself. Many people would use a thesaurus in that situation, but perhaps they just can't think of a word that's anything like the word they want. They can only think of describing it in very plain terms. And in that case, we can just apply this model, feed forward. Once it's trained, we can feed forward through the network and retrieve the nearest neighbors, according to cosine distance, say, from the pre-trained word embedding space, right? So because it's slightly more fun, I'll do it with a live demo. So the example here I've got is a way to describe something sticky. So I just chose that as an example of something you might want to search for if you were a writer. That's not the... OK, right, it's updated. So the models I've got here then, one look is a commercial... Is that big enough for everyone? OK. So one look is an existing commercial product, which I think uses... So it's not public knowledge exactly how it works, but it uses a classical information retrieval approach. So it indexes lots of dictionaries and then tries to match the input to an existing definition and then retrieve the word that corresponds to the closest definition. Word2vec add is a really crude baseline in which we just add up word vectors and retrieve the nearest word vector. So it doesn't work very well in any of our evaluations. But there is some evidence that adding up word vectors gives you something sensible, so we at least tried it. Then we've got the RNN and the bag of words model. So here these are reasonable candidates, right? This is something that as a writer you might benefit from. You'll notice that there's not a big difference between the RNN model and the bag of words model. So that is one application. And of course, there's a nice way to evaluate the different models in this framework, which is just to evaluate retrieval performance on the held out data. What we actually found is that, strangely, the best performing model was the bag of words model with the pre-trained embeddings. We divided up the inputs into different tranches of lengths. And the biggest impact is on shorter inputs. So intuitively, that makes some sense because we know that we can add up these word vectors in this space to leave us somewhere sensible when we're adding up a small number of vectors. And so if we already have the pre-trained embedding, the model really doesn't have to learn a lot in order to get to a sensible part of the space. It just has to learn a little bit of tweaking for 2 or 3.
One look do so well here, whereas in the previous example, they don't seem to work well.
Yeah. So I'll talk more and more about the differences between OneLook and these continuous models. But it's true that in the evaluations, OneLook does quite well. But everyone I've spoken to, and of course I'm a little biased, but everyone I've spoken to says that the performance on the web demo, it doesn't seem very good for OneLook. So it doesn't. No, so okay, yeah, so that's a really good point. So I'm not sure about that. So in this evaluation, I can't be sure. I can't be sure what's in the OneLook data, and I took publicly available dictionaries to make my test set. So it's possible that that's in the OneLook data. What I would say is even on things which I know are not in the OneLook data because I made them up myself, OneLook still performs okay, but the users don't seem to like it as much. So it's a soft sort of difference in quality.
No, you just have to scramble your test set, maybe choose different kind of test set to see whether
it's hard to find. It's hard to find any dictionary definitions that I'm sure are not in here, basically. Yeah, so one really interesting thing is that bag of words model does so well. Clearly, word order should be useful in interpreting what definitions mean, but in this case, it must be some sort of regularization effect, right? So remember, this is on a test set, so this is testing generalization. And perhaps the fewer number of parameters in the additive model just allows it somehow to make it more robust to generalizing.
But also maybe this particular sentence, if you scramble it any which way, it's still going to be clear. The intent is still going to be clear to the human. So why not to a machine? Why bother getting something out of the order of the words when the order of the words doesn't matter to you in this case?
Yeah, absolutely. I'd be very interested to compute how often humans can do this when the word order is scrambled, and I think it's much more often than we might imagine.
Try the test set to break up into long versus short, just to see whether RNN changes. Yeah.
So, I mean, that was one of the first things we did because we actually wanted, obviously, we had a sort of slight prior desire for the RNN. This was also when there wasn't too much applications of RNNs for language understanding. Now it seems kind of old-fashioned, but it was only like 2 years ago or 18 months ago. But we had a sort of latent desire for the RNN to perform well. We just couldn't show any clear benefits. So it could be a fact about how the information encoding in dictionaries and definitions.
Are the words held out, or is it just the definition is held out? Can it retrieve things for novel words that were not in any of the dictionaries, but still in the word embedding corpus?
Yes, yeah. So the candidates it can retrieve, many of these words may well not have been defined in the training set. Yeah, the word embedding space it spans many more words than what are defined by the definitions. But another way to improve performance, of course, a trivial way, is to then prune that space based on frequency. So somehow very low frequency items in that space will not be in a dictionary. And so taking them out of possible candidates improves performance. Yeah.
Have you tried the other way around? Come up with definitions of words?
Yeah, that's a really good question. So I would love to train this as not really a generative model, but as a conditional RNN that samples from a vocabulary and generates text. I tried it. It didn't perform very well. So, I mean, just qualitatively on my intuition. So I think there's a number of possible explanations. One is I'm not an expert on optimizing these models for generating text. I know that there are experts probably here. There are other people who've worked on machine translation would be good people to talk to about that. So I'm not sure whether I just haven't got all the hyperparameters and everything right, or whether it's genuine fact that it's hard to generate dictionary definitions conditioned on word vectors in a way that it's not hard to generate, for example, captions of images conditioned on image vectors. So that is relatively easy. But if you think about it, the word vocabulary in image caption generation is pretty simple. So humans are being asked to give a simple description of what's in an image, and they probably use common words. In a dictionary, I think you get into really quite a much bigger vocabulary of complicated words. So then generating a good definition is hard.
I think perhaps the intuition would help you, that a dictionary is about, you first identify what are the genus, and then what differentiates it from the rest of the space. And so dictionary definitions are very carefully formulated to find kind of, okay, what's my hyperterm, and then how am I different? And that, I think, would, if you design that in how you look through the space, you might get better definitions.
Yeah. I mean, for me, one of the fascinating facts is even if it is formulaic like that, the model doesn't seem to learn it. It could, It also could be that I haven't. One of the downsides to neural nets is sometimes you don't know whether it's because the model can't learn or because you haven't searched the hyperparameter space enough.
Result slide. So that's at 10. Are the patterns, is the trend similar as you go from less, like 1 to 5, 10, 20?
Yeah, I didn't see anything systematic. And again, I tried that because I was sort of exploring ways to see the differences between the models. So 10 is obviously kind of a natural. 10, I think, corresponds to maybe the use for a human. So I think getting 10 candidates could make it a useful tool.
Behavior did not change.
No, nothing that I could see that was a clear systematic trend.
Yeah, you have to do what the question is. I think better architecture would be like denoising autoencoder, right? Where the word for definition will be coded as bottleneck, whereas the definition could be input and output. And then once you do that, then you put some noise there, then you can just sample from whatever.
Yeah, right. And it could be no, and it could so you would have to
draw AW that with the recurrent version of the denoising autoencoder.
That's learning both the encoding and encoder, learning encoder together with the
encoder.
The decoder, yeah.
But in the training phase, you
because he's using already existing embeddings, maybe it's difficult in Word. Is that what you're saying?
Yeah. No. What I'm saying is that the definition, is the long one, is the observation and also the target.
right.
And then you, somewhere you put some on the noise encoder kind of know to corrupt some of this. Therefore, you can learn some generalization.
But then he will learn a new embedding in the middle.
No, but in the middle, the middle one
to
has to be constrained to be the word that you define, the definition of the word that you want to do.
Okay.
And in that case, I think it would generalize.
Okay.
To give you some description that varies from the original one. Therefore, for the new one, you probably.
But it also depends on what you mean by failing, right? Because naively, if somebody doesn't know anything about this area and says, well, it's question answering, you can ask any question, you're going to get an answer. So you can say, what is gluey? And you'll get an answer, some sort of an answer. So how do you, when you say it didn't work, in what sense it didn't work? It did not produce a sentence that makes any sense,
Yes.
so it did not produce a sentence that explains the word.
A bit of both. Yeah, so I guess, you can sort of informally break down generation into two things. Do you get the information you want, and does it produce it in a way which looks like language? And it kind of failed on both counts. Yeah, but that's not, I don't want definitive conclusions to be drawn from that. I think I haven't explored it long enough. So one way we wanted to sort of try and tease apart the difference between the continuous embedding models and the symbolic one-look model was trying to see how far we can generalize away from the training data, right? So if you start putting in queries like this, a habit that would annoy your boss. So clearly this is, yeah, so clearly this is something that is not in dictionary training data. No word would be defined in those terms. But you can see that it comes out with pretty good candidates here, right? So Wandler is done terribly at that. Okay, let me zoom it in. Yeah. So here are some things which could annoy your boss: bossiness, swineness, petulance, grumpiness, malignity, surliness. So they're quite good candidates, right? And then you can start playing with it to see to what extent it knows something. You can change the word here. So this one's quite amusing. A habit that would annoy your spouse. So, oh, excuse me. Okay, so here we get unfaithfulness, infidelity. See, boorishness, you get these hubs in word embedding spaces where the same word appears again and again, which is quite strange. We get rudeness, immodesty, promiscuity, jealousy. So these are all actually really quite good responses. Now, clearly the bag of words model. So, I mean, I can.
And how about here, if you're going to want to go back to the language? If you ask what annoys you about your spouse, would you get the same answer?
Yeah, let me try that. I'll just quickly show one thing, right? So here I've changed the word order completely. A spouse that would annoy your habit. Bag of words doesn't change. Okay. RNN. It's still not that. Yeah, it's kind of odd, I suppose. So RNN's obviously got some sense of the word order. And then what was the one that?
It's just like how do you know your spouse?
So I've got a sense that it would be quite good at this one just by the same sort of, yeah. So a slightly different part of speech here, which is quite nice. So there it's answered them with a verb rather than a noun. So that's quite nice.
And then the previous one. What annoys you about your spouse?
But,
It's different.
yeah, so it's, clearly it's understanding language in a very thematic sort of topical association way. It's not chunking up the meaning into sensible chunks and coming up with answers that we can be certain of. But the way the concepts interact is quite nice, and it does lead to a part of the space where the word candidates are actually combine things in a way that we actually find matches our intuition.
In this case, RNN clearly disambiguous between these two things.
Right.
And it's the same word, it's just different order, more or less.
Yes, yeah. So the RNN does have a sensitivity to the word order that the bag of words model doesn't.
Just end up on a positive note.
Okay, right. So not so good at this one. And actually, one look is quite good here. Yeah. So, I mean, love is probably a nice one. But there's a real mix. So yeah, I mean, it's a mix. Yeah.
I didn't mean to break it.
No.
Kind of
It's very easy to break.
I was playing with the polarity of it.
Yeah, I'll break it myself as well in a minute. But yeah. Okay, so then a final question was, in these representations, so to represent any phrase now, what we can do is feed it forward through the train model and arrive at a vector, which hopefully summarizes the meaning of that phrase. So, okay, before I mention that, another quick application. These models are actually quite good at doing general knowledge crosswords, right? So in the UK, at least, we have these quick crosswords, which are not like the ones where you have to have a really good knowledge of how to do crosswords and you know all the tricks. They're actually just basically like a quiz in a grid. And importantly, for people that work on real question answering, these are a certain type of quiz question that corresponds quite closely to like the defining properties of concepts rather than secondary information about those concepts and things. So it turns out that they're quite good at this. The bag of words model again is better on our evaluations. Here I just took a quiz at random from The Guardian on the day I first did this talk. and I scored the models. So the one is the top, it gets the top answer first, and this is the place in the ranking where it got the first answer. And then a blank here is outside the top 10.
And you're taking into the account that it's puzzle, the overlap?
No, absolutely no consideration of the grid, but there is consideration of the word length. Okay, but they perform quite well even without the word length. This obviously massively constrains the search of words. It's not surprising that they got this one right, because amongst 11-letter words, there's not many candidates, right? You've then got very few. With 6-letter words, you've got many more possibilities. If anyone knows about optimizing like sort of grid search over a crossword and letters, then I'd be more than happy to collaborate on turning this into something which can actually complete the crossword. But
Is there a crossword data set?
I think there must be data sets, but this is a non-linguistic problem about optimizing a search, and
14,322.
yeah. Actually, I mean, you could probably scrape these. Yeah. But I'm not sure what the value of really getting good at these is automatically. And actually, one thing, I spoke to somebody who does like to do this automatically, and he said that the gains in the language candidate generation part are so marginal compared to the gains of getting better at searching the grid optimization based on vocabulary of English. So probably it's not worth pursuing just for a crossword answer. So how good are these models in the general purpose sense of learning phrase information which encodes general knowledge information which we can then apply at a later stage to a different task? So here's a little range of language sentence classification tasks. Okay, it's chosen to match the range of tasks that somebody else, so there was a paper called Skip Thought Vectors about sentence representations, and I just wanted to match the evaluations used in that paper so that we could leverage their comparisons and then make more comparisons. And it turns out that this is what I called supervised evaluations, because each of these evaluations involves putting a classifier on top of the representation as pre-trained features and then measuring the performance. The dictionary model with a bag of words pre-trained embeddings is quite good at these tasks. So it outperforms other models on MR. I'm trying to remember what MR was. MR was a particular language classification task. This was customer reviews, so classifying customer reviews into positive or negative. And then this was a question-answer classification data set, MPQA, and TREC was the same. So 87.2 was a reasonable. So essentially, in this sort of suite, this is all a bit of a mess in terms of understanding which models represent phrases in the best way. And it's quite hard to tease apart the differences in the models. But this gives us sort of an intuitive or circumstantial evidence that these models have maybe embedded some sort of reasonable level general knowledge into their space. A more easy to understand evaluation. Skip Thoughts is here, and it does pretty well. I've also, some of these other models are ones that I've proposed myself. I'm not going to talk about them here, but we can talk about them over the course of the next couple of days if anyone's interested in general sentence learning architectures. Skip Thoughts is the best on 3 of these 5 evaluation sets in our evaluations. Okay, a more intuitive and easy to understand thing, although possibly less useful, is how well do these phrase embeddings correspond to human intuition about which sentences are similar? Of course, this is one of the most noisy ways to evaluate anything because sentence similarity is terribly defined and the human annotators on these rating tasks don't agree at all. And so it's really just a very high level way to evaluate things, although people do publish papers just comparing on such data sets, which is a little bit odd. But we compared ours on the sentence similarity tasks as well. And the dictionary representation model is again amongst the best. Now, of course, many of these models are trained on just plain text. So the dictionary model does have a much stronger signal to learn from. So maybe it's not surprising that it represents phrases in a way which humans would agree with.
I'm not quite familiar with how you set up your model, but in the end, do you end up getting a distribution over the space, or do you get really just peak at one spot?
Yeah, just peak at one spot, yeah.
So can you make a distribution in some way through sampling?
Yeah, I'm sure that there might be a way to get. So one of the many things that can be improved about these continuous valued models is that they do represent linguistic type as a single point in a space. Now that's already a nice amount of information compared to a symbolic representation, but there's actually, it's maybe not the most refined representation considering how meaning works. So we might like a representation to be dependent on context, so more like a token-based representation, or a representation to be probabilistic in the sense that it's a distribution we sample from. Yeah, that could lead to a more satisfying model, I think. Okay, so a few takeaway points from this section. We can use dictionaries as a way of understanding phrases and encoding general knowledge in these continuous valued models as much as we can use them just by retrieving from them in a symbolic sense. It's reasonably possible to store sort of rudimentary general knowledge in these distributed memories, which is interesting. So yeah, we can actually answer some general knowledge questions in this way, but of course, nowhere near the full range of general knowledge questions that a question answering system would need to answer.
I mean, one of the problems with the distributed representation, it may overgeneralize. That happens all the time. So in your demo there, if you actually put the exact phrase in the training set about particular definitions, sometimes if you use a symbolic one, you probably get it right right away.
Yeah,
but
absolutely.
for distributed representation, do you always get it right, or
No.
do you?
Yeah. Performance, essentially performance on the test set. I mean, the symbolic model is probably not even learning, but performance on the test set is close to 100%. In our model, performance on the test set is not that dissimilar from performance on the training set.
So
right.
You probably overgeneralize too much in distribution. So there must be ways of combining symbolic and distributed in such a way that you can.
Exactly, that would be perfect. So the smoothness of and there's ways where you can measure the smoothness of the candidates as well. So there's kind of like, if we measured the variance of the rank of the correct answer for the models, and the one-look model either gets it right or it gets it terribly wrong. Whereas the continuous models have more smooth output in the sense that the ranking of the correct answer moves around between 1 and 100 or something. So that smoothness is a quality which I think we can benefit from for language applications, but obviously combining it with the fast retrieval and accurate retrieval and all these other properties of a symbolic models which might be necessary in user applications, yeah. Okay. I'll talk quickly now about representing sentences in context. So it's one of the biggest challenges, but if you see this, it's one of the biggest challenges without any context. It doesn't make a lot of sense. If you know the sentence before this sentence, then it's easier to decode this sentence. It's easier to interpret it in some way. Here, the reason is because of anaphora, right? So here the it corresponds to something in the sentence before, which means it's very clearly required in order to make full sense of this sentence. But even if there's not anaphora, it's an open question the extent to which we can interpret any sentence in a meaningful way in isolation, right? People don't use language like that in general. So one of the things about neural language models is that they've worked generally on a sentence-by-sentence basis, and we wanted to explore ways of extending this to a wider scope. To do so, we created a new data set. I should say that, like in MSR, there's been, like, as I understand it, lots of amazing data sets created. So this is kind of an extension of one of those, and I'll do a little comparison in a minute. So we called it the children's book test. So it's very similar to the Microsoft Research sentence completion data set.
So is that the one that Facebook just?
Yeah.
The one they're using.
Yeah. So this was work at Facebook when I was an intern there. So it's very similar to the sentence completion challenge. It even uses the same underlying corpus of text, although we focused on the children's section of the Project Gutenberg corpus. So the only real difference, in case you already know about that corpus, is that the only substantive difference is that here we've also released the context, which is what we call the context. So it's the 20 sentences before the sentence where we need to complete it, right? So yeah, we've got what we call the context. It's 20 consecutive sentences. The query, I've called it the query. It could be understood as the question, but for me, I'm going to use the word question for the whole of this thing. The query is the 21st sentence with a word missing. The candidates, so I think in that data set there are 4 candidates, but we've got 10 candidates. We just wanted to make it a little bit harder. Importantly, all of the candidates occur in the context, and the answer also always occurs in the context. So that's what a training question looks like. Okay, we also divided up the questions into 4 types. So in one case, prepositions were removed. In one case, verbs were removed. In one case, common nouns were removed. And in one case, named entities were removed. And when we created the candidates, they were randomly sampled from words of the same type in the context. Now, in the case of named entities in particular, we couldn't get 10 candidates from the previous 20 sentences in general. So there we filled them up with nouns. And there was kind of a back-off going this way in case we needed to fill up the candidates. But it didn't happen very often apart from for this category. So in this category, you're essentially guaranteed to have all of the named entities amongst the candidates. But
Yes,
some...
So I don't have problem with this task. I mean, so the SALR conference, people talk about this, right? So since you were involved in designing this task. So basically, when you actually constrain the answer to any of the questions to be something that appears in the text, it really reduces the problem understanding to something like a classification.
Right.
And that's not very good.
Yeah.
I mean, even if you succeed on this, it really doesn't count that it's a good understanding. Ideally, just open up the question and then you answer whatever you want.
Yeah.
It doesn't have to constrain anything. So what is the design philosophy? From Facebook, they want to put this kind of control.
Yeah, that's a really good question. So I think one of the things is that obviously the question wants to directly test how well the model can use the context to find the answer. So now, of course, that's a classical information retrieval thing. It could also be construed as like a named entity matching or an AFRA resolution thing. There are many ways in like previous approaches to language processing which you can understand that task. I think Facebook specifically wanted to try and test their neural sort of memory-based models on such a thing. So they created this new data set. I completely agree that if the answer is not in the context, that's kind of a more open and more substantive problem. Yeah. But one thing I'll say after I've explained our work is that since we did our work, a model has, well, our work kind of already demonstrated ways in which you can kind of shortcut the general problem to solve our task. And then another piece of work has gone even further and really shortcut the general problem in order to solve the task for the exact reasons you described, which is that they know the answer will always be in the context. And in that case, yeah, that's a bit unfortunate in the sense that that solution maybe is not one that we would like. But it's a great piece of work because they've just solved the task in a really nice way. So, well, we can easily, modify this task and generate more questions in which that's not the case, and maybe intersperse them. And so, yeah, there are definitely potential to improve and extend it.
Is it also the case that, so for the verbs, for example, say that the correct one is heard. She heard the story on the train, and if without this constraint, the model had proposed overheard, it's very hard to score that automatically. So is it the case that some part of the design is also formulated because you want to be able to do automatic evaluation?
Right, exactly. And of course, yeah, I mean, if you have the open-ended model, you're faced with a choice of like a sort of perplexity evaluation, but then with perplexity, that's a function of the model itself and the number of candidates it has in its own vocabulary and all these other things. So this kind of constrains it. But I agree. I mean, one of the big compelling problems about language is that there's no single right answer. This kind of cheats and invents a single right answer, which doesn't solve the wider problem of there not being a right answer. Yeah.
So how dependent is you try to sort of quantify how dependent this task is on the context, because many of the answers would just come from a language model, right? Even the last one, the named entities one. Baxter is a last name, while the others are not last name or their first names, and so you would say Mr. John. That doesn't make sense, right? Mr. Baxter, okay, that makes sense.
Yeah, that's a good question. Thanks. That's my favorite type of question because I have the answer ready. So, but okay, yeah. So we got a lot of data here as well, right? So data for training, data for validation, and data for testing. This is a sort of shout out to work that went before, so that it's clear that I'm not sort of trying to sell this as anything particularly novel. So yeah, this was the first piece of work. We've added context to this. We've added the different word types, and we've obviously scaled it up a lot. But this was a really, I think, really nice first piece of work to make language modeling evaluation a lot more principled. You can also compare it a little bit to the MC test, which is this machine comprehension test where humans wrote a story and then some questions. Again, the main advantage of our work is just scale. We've got many, many examples because they're automatically generated. But this is a more principled test of language understanding, I think. It's just that there's very few examples. We've tried lots of models on this data set and we couldn't get anything working well. And the best performing methods here use a lot of hand-coded features, and so it maybe didn't work with the neural language models. There's also this data set, which was released by Google DeepMind, where they did something similar to us, but their query was a sort of, in a news article on a website, there's some summary bullet points at the top. And the query, the word was removed from that, not from the story itself. So that has some advantages, but the disadvantages were two. Well, one very practical one was that this wasn't publicly available. So we made another one. It then became publicly available. Another clear thing here is that they've anonymized all of their entities. They've just given each named entity a code, which we wanted to see if we could have models which also use general knowledge from outside the context. We wanted to allow that as a possible way of solving the problem. So for example, a model which looks up a concept in a dictionary or does something like that, or has some visual stimulus it uses to improve. So it's not so possible if you anonymize the named entities.
But this is much bigger, is it? Yeah. So
This data set.
much bigger, right?
This is a good data set.
Yeah.
I think so, yeah. Yeah, this is also a really nice data set, but it doesn't allow so much analysis. So our model has different word types.
So does this task require that the answer, the constraint, the answer to be part of the text?
Yes. Yeah, this has the exact same limitation that our model has. Yeah. There are no questions in this data set where the answer is not in the text. Yeah.
How many choices do they give? It's like a multi-choice evaluation or
It's somewhere in between the two, because the possible so everything here but works on named entities. So for any news article, the named entities are all anonymized, and then the correct answer is known to be one of them. So the number of candidates is effectively variable in that task. And it could range from 2, I think, to upwards. Potentially, although it would be very rare to have a news article with 100 named entities, I guess, but it could do, yeah.
I see for children's book test, the answer is always considered to be one single word rather than allowing for you to have a phrase.
Yeah.
They don't.
Yeah.
So neither does this.
Neither does this. Oh, well, actually, no, that might be wrong. So yeah, it functions as a single entity, but it may well have been taken from,
It's more fair, more general, right?
It's more general,
So you don't have to, I think the problem I have, with this CBT is that ultimately you just, get classification problem, right? Whatever, number class are there, single word. But if you can allow for combination of words, the class becomes so large that you won't be able to treat that as a classification problem.
And that would be a nice way to extend any of it. So the children's book test, we could also omit small sequences of words. Yeah, that would be quite, and then we could also have candidates which are generated in some principled way as possible small sequences.
Before, not to take the standard classification approach to solve.
Exactly.
I think that would be.
So quick aside, something that I feel quite passionately about, so I'm going to mention it. Evaluation it's good because I'm here at Microsoft, and a place where they've created lots of very important and good evaluations for language technology, but I still think it's one of the most important things on the path to getting really good human-like language understanding is really principled evaluation, so that the community can then come together and try and turn their attention in the right direction. So we have a workshop at ACL this year where we're discussing the problem of evaluation, probably for the millionth time in the history of these things. But if anyone has any desires or ways to share ideas, then it would be great to hear from people at ACL or even just by email. One thing which I think is quite a nice principle, so lots of people are frustrated that neural language models perform very well on lots of tasks at the moment, and I think one way to mitigate this is to get a sense of what sort of questions are most important from our models. So if we sample test sets more sort of uniformly across the frequency spectrum, we might be challenging models to do slightly better at rare or unusual things in language. And those things, maybe the neural language models with sort of complete lack of structure, they might not perform so well at those things. But information theoretically, at least, some of the most important language is in these rare things. It potentially carries more information. So what we've done with the children's book test is sort of divide the missing word types up into different types. And what it tells us is that different models do differently at different things. So it's a sort of a version of this with the different word categories. But doing this in general with a test set may well be very important for language research, I think. So anyway, how do humans do? So this goes back a little bit to what Pushmeet was saying. So if we give humans only the query, so only the one single sentence with the missing word, then they perform like this. So they're quite good at prepositions, they're a little bit better at verbs, they're a little bit worse at common nouns, and then they're quite a lot worse at named entities. So you can see why, even though in here a human would know that there's probably only 3 possibilities, they might, or even 2, because this is probably not a surname, they still would have only 50-50 chance, right? Now, if we then add the context, human performance changes, right? So then they're actually best at named entities, and they're worse at prepositions. This is actually quite laborious for a human to do. So we did it with lots of annotators, but it's boring. Reading 20 sentences and finding the right answer is quite boring. But this is interesting, right? So humans can't actually do prepositions perfectly, but then I think the reason is that in many cases, more than one preposition is correct to a native speaker, but obviously only one is correct in our evaluation.
But this one depends on how much answers.
Are these all English?
Exactly.
Speakers?
Exactly. Yeah. And so what's really interesting, actually, we'll see. So here this again relates to what Pushmeet was saying. These are sort of classical language model approach, right? So just train a language model on all the text, and then at test time, feed it forward through a part of the problem, and then compute the probability to the end of the query, and then give the candidate word with the highest probability. Now, if the difference between, the difference between green and yellow is that yellow, it was initialized to answer a question, we feed through the whole query, and then feed through the whole context, then the query. So in the case of an LSTM model, we're asking the question, how well can you remember like many, many sentences back? What we see is that these models are better than humans at prepositions. And this is exactly the point, I think, because these models trained on the training set, right? So they're then attuned to this type of English. But a human has got its own type of English, and probably not 18th or 19th century English. So, yeah. So
But you could train language model using lots of other data as well, together with that data.
Yeah.
And that's not the one in blue.
no. We wanted to sort of keep the evaluation close to the training set just so we can compare all the models. But there's no reason in principle why we would need to do that. What we learned from this is that so if you smudge together all word types in a big sort of mush, then these models look like they're performing really well. But that's what perplexity does. It's average perplexity over words. But actually what happens is the models are just predicting these half the time because these are the most frequent words. So what looks like really good human-like performance is not, because these models are not performing well on named entities. They're a long way from human performance. And then common nouns also.
But the human performance really depends on how much time you want to give human to solve the problem.
Of course.
If you give them a lot of time, of course they probably get 100% right.
Yeah, so it's a question about,
So
it's not about reflecting how it works with human processing. It's about just, is the information there in order to come up with the answer eventually. But yeah, there's nothing sort of naturally cognitive about this task and the way humans do it. They do it in a very searchy way.
A set of bars, right, which is the context-less human. The human which was not given the context.
Yeah, you're absolutely right. So this is humans with access to context, and I think it would go. It was going like this, down, but still nowhere near as low as this.
This is sort of surprising to me in the sense that if a language model, a pure language model, really had done its job correctly, right, and if it even had sort of notions of what could be first names and what could be last names, then it would have done significantly sort of better, because like it is doing well on the prepositions and verbs, right? The context-free language model, but it's not doing on the named entities. So which says that there is something missing in the pure language models.
Yeah. So there's two factors I think at work. One is that these models which build up, especially, so it's not true of the symbolic n-gram language model, the KNLM model. But for the neural language models, they randomly initialize vector for every concept. And to build up a concept of an infrequent thing like a named entity and get any sense of how it operates in relation to other words, it would need to see an awful lot of language. The other thing is that not only at test time, if we use perplexity, are we mushing everything together, but the raw objective of the model, which is like maximum likelihood training on replicating a text, that also massively incentivizes getting good at these things in relation to getting good at these things. So actually a fairer test, which we didn't implement, might have been the exact same architecture where you only backpropagate on this word type. And that would have been, so that's not, we didn't implement that partly because it wasn't our solution, and it wouldn't have, but it probably could have been a fairer baseline in a way.
When humans are doing this task, do they read the text first and then they get a question afterwards, like the way you test kids for reading comprehension, or do they have the text there and they can refer back to it?
They have the text there and they refer back to it, and I'm pretty sure if you have an eye tracker, you'll see that they read the question first, and then they work backwards. Maybe not the first one, but once they've done 2 or 3. Yeah.
And the protocol was for collecting the ground truth that the human is given the query without the context. They give the answer, then they read the context, and then they were asked the query again. Or were these 2 separate humans who were? Because you collected 2 answers, right? One with the context and one without the context.
Yeah. Separate populations of humans. Yeah. Like crowdsourcing. Yes, between the 2. Yeah, exactly.
So I just assume that name entity here is a one single word rather than a word phrase.
Yes. Yeah. We didn't do any of the chunking together of named entities. Okay, so our solution, which was a model which already had been applied by Facebook to other things, was this memory networks. It's a sort of general approach which can be used to describe a number of attention-based or conditional language models, but the way we implemented it was like this. So we first form an embedding of the context, or we form multiple embeddings of the context, which each occupy discrete positions in a memory, what we call the explicit memory part of the model. We then have a feature map which learns to represent the query itself in a different part of the model. This is called the query representation. And then so these vectors are of the same length. So we can do a dot product and compute a score, which essentially scores a match between this and each of these locations, which gives the model, which tells the model how important each memory is. That's what the model needs to learn to do with that score. And then we get this could be thought of as an attention mechanism, but it's essentially just a series of weights weighting each location in the memory. The length of the memory was a hard-coded hyperparameter, so this doesn't scale in its current guise.
So the original of this model is based upon word or backup words in that encoded one. And later on, it's to distribute it.
Yeah, so even in our model, we had a small trick to weight different features, but we didn't use an RNN here to encode the sentences. So there's still a bag of words representation going on at this stage. So it was more of a test of like a quick test of where the information is, rather than optimizing for the best sentence representation here in order to really improve the model. Yeah, there's a lot of backpropagation. There's a lot of layers of this network. So it actually probably would be possible to have a really involved sentence representation here, but we didn't do that. So then, using the attention, which is weighting each location in the memory, we then just do a weighted sum here, right, to get one single vector out of the memory, which hopefully represents the important semantic content of the memory. We then add in the query representation again, and we arrive at a prediction layer, and then we can make a prediction in the way that any language model makes a prediction. So we compute scores across the output vocabulary using a softmax. So we have an output representation for all the words as well.
What was the architecture? Okay, you're going to go into the architecture.
Yeah, the specific representations I can talk about more. So, well, yeah,
So how does, for example, how is the context representation mapped to the prediction layer? Is it a convolutional structure or the fully connected structure? Or
so here, this is fully connected. So essentially, we just compute the model. So we tried various things. There are ways of different sharing weights. So we can either have this representation be a totally separate representation with new weights, which forms of the query representation to add in here. And then we have a different query representation, which is used to compute the scores of the attentions over the memory. So
you have only 20 sentences.
right.
You have a fixed number of sentences, but if it was variable number of sentences, then how would you deal with it?
Yeah, I mean, we would have to have some sort of either pooling of this to get to a finite length, or recurrent model, some tied weights in order.
No, you know what? Backward model, it doesn't matter. I mean, the length ideally would be the vocabulary size. And then it doesn't matter how many words you have, it's just, 0 and 1, or 2 or 3, whatever
Right.
will come.
Right.
So that vocabulary size, so when you say that the length of the vector is hyperparameter, you mean that for some rare words you get rid of them.
No, sorry, there are various. There are various hyperparameters, I guess. So one is the length of these
Yeah,
representations
that would
here.
be the size of vocabulary, right? When you use the word of a backward model.
Oh, okay, no, so it's not bag of words in the sense of being like a sparse vector of distributed. These are distributed representations. This is an embedding. It's a bag of words model in the sense that the feature map, which is used to get to this embedding here, either can or cannot take into account word order.
Oh, I see.
Yeah. At the sentence level.
But it doesn't matter whether you have 20 or 10 sentences because you're averaging those in the end.
Exactly. Yeah, you're absolutely right, Nabushi. So yeah, there wouldn't need to be any recurrence because there's a sort of average pooling here, basically.
So you have another neural network to map from backward into that vector.
Yeah, you can think of it as an embedding layer or as the first layer of weights in a network if you draw it all out. But so I mean,
Done by backpropagation all the way.
all the way, it's
Okay.
end to end. So there's one error signal optimizing this whole network. So it's all continuous feeding into one. If I just, it's a bit of an aside, but I do have the various ways of representing sentences that we tried. It wasn't by any means exhaustive. So the first was what we called lexical memory, which is literally just putting in each word into a slot in the memory. So this was really kind of a strange thing to do in some sense. The second thing was what we called window memory. So here we have a sort of almost a convolutional thing where a window moves across the context. And we fix that window at 5 words. But you could also, so in other architectures, they've used a bidirectional RNN to read the context from both directions and taken the hidden state at a concatenation of both directions, hidden state at each point. That actually gives you something a bit like a window, a soft window that's slightly variable. And then finally, we can try and mush all together each sentence into a single representation. This doesn't work very well. The one that works well is this. Okay, so it seems to give you just about the right amount of information. Even if there are many windows of 5 words through this context, right? So we have a lot in the memory, but even so, it seems to perform quite well when we do it like this. And
Does this preserve sentence order?
yeah, so we do have a way of telling the model where these memories are. That's not just like. Yeah, so we have a sort of a temporal encoding in the memory at this stage. We can add that with a separate embedding matrix, which essentially gives the model a little bit of information.
That is the question I wanted to sort of ask, right? Because like when the final sort of question appears, it might have a different answer depending on which order the sentences were presented.
Yeah.
It might be, right? It might be that might be a possibility. And then the question is, like how is the order sort of encoded? And if the order is encoded, like at some, you will have to have a convolutional structure, right? You cannot, or you have a fully connected structure, but then you're assuming that it's a constant definition representation.
Yeah. So we do have a way of allowing the model to learn to take into account order, essentially. But it would be interesting to analyze where it does. So I'll quickly I'll speed up a little bit so we can come to the end. Okay. Yeah, sure. So the memory network model performs this well, right? At the initial version that we tried. So it's not so good at prepositions, not so good at verbs as the classical language models. It's about the same at common nouns, and it was a little bit better at named entities. So essentially what this model is doing is it's bypassing some of the backpropagation through time that the recurrent language models have to do. in order to get an explicit view of the context. And it can learn to retrieve a little bit better from that because it's sort of shortcutting some of the backpropagation through time. What we then found is that the best way to get good performance on this task is a little bit like this shortcut approach, which kind of relies on the right answer being in the context. So it was an additional training to give the model more signal. So if we just train this part of the network using maximum likelihood to select, to give highest probability to the correct memory, right? Then we actually then can continue training and alternate updates with this model and the end-to-end model and get better performance. So somehow training the memory is the hardest part of the optimization. And by giving an explicit signal, we can improve performance. Now, how do we know what the correct memory is? Well, we just invented a heuristic, right? So this is where it gets kind of hacky. The correct memory was the memory that contains the correct word. But of course, there can be a case where multiple memories contain the correct candidate, right, in all of our different memory architectures. So in that case, we feed forward through the model the training case, and then the memory which the model would naturally compute a score for the memory, for a distribution over the memories. The one which is allocated the correct score, we then take that as sort of factual information that that's the correct memory, or provided it also contains the right candidate. We then perform a gradient step where we update based on maximum likelihood. Essentially, it corresponds to just updating the weights in this embedding matrix and this embedding matrix, the input embeddings. But it means that the model is certain to be looking roughly in the right place. Once we do that, we get even better retrieval of named entities. Now, since our work, a model which essentially consists of just this has done even better on both our task and the DeepMind dataset, because that also has the same property. So this goes back to essentially this being just a classification task. You're basically saying rank these words or compute a distribution over this context for what is the best thing to look at, and then select that thing.
What is that model?
That is called the Attention Sum Reader Network, and it's by IBM Watson team in Czech Republic. And the reason they beat us is because their representation of the context is better than ours. They use bidirectional RNNs, and that archive, and it was a workshop paper at ICLR.
ICLR, right. So this work is also presented at ICLR?
Yeah.
Okay. We step up. Also,
Yeah.
IBM's one is better than this one because of they also use the heuristic label.
They use this, but they have a nicer sentence representation. So we have hard windows of 5 words. They had soft bidirectional RNN windows. That seems to be the deciding factor.
Which label, that depends upon how ambiguous that labels are, right? As you said that there are multiple.
So because we used windows of 5 words, we needed a heuristic to break ties in the situation where the correct answer appears in different windows. They used a bidirectional RNN, which meant that actually they don't need to break ties because only one of the situations is the word that they're looking for. So I think that they didn't need the same sort of heuristic. They just trained the network to find the right answer in the context, basically, and that's exactly what they're doing.
So in MC test, their baseline evaluation is actually just using word matching to find the sentence and then. Yeah.
We applied the baselines from MC test to this data set. They don't perform as well as any of the models I've described today. Yeah, so that was the first thing we tried.
Very similar to the idea of selecting the right sentence.
Exactly. So I think it's probably good news that these embedding models at least do that, but with a slightly better generalization, and so they perform better. But yeah, we did try very simple baselines on this data set.
So this diagram does it mean that you don't need to have to do multiple times, just one single shot? So one layer, no need to the memory.
For their approach.
For this approach. So it looks like there's no multiple.
Yeah, there's no multiple access of
just one single.
Yeah,
Oh
exactly.
wow. Okay, so the label probably is more important.
Exactly. Yeah.
So what about if you're during training time you infer which one is the best memory representation and train the parameters that way, and then later you train the system using heuristics? You see what I mean? Like all of these things seem to be avoiding explaining away, and eventually you have to do explaining away.
Right.
And training time, you could do explaining away. You can treat these weights as, selection mechanism for which memory representation to use as a hidden variable.
Right.
You can test which one works, and you can train that way. Now you're left with the task of being able to recognize which of these variables is the correct variable at the test time, which you can train as a separate process.
Exactly.
So closer to the real explaining away.
Exactly.
How long would that work? I mean, have you thought about it? Have you done that?
No, but you're absolutely right. You could then set up a model which built on top of this to take the output of like what seems to be the right memory and make a prediction. And you could actually you might solve the problem in that modular way better. I've got a feeling you probably would. I would use the IBM architecture to do this bit because it's slightly more elegant than ours. But then on top of that, it would just be a separate model. Yeah, that would be quite a good. And ultimately, I think I was chatting to those guys, and they suggested that IBM would like to use that as some sort of question answering application. If they need to do that, they will have to add this bit on that can basically knows what to do in a situation where the answer isn't in the text or something like that. Yeah.
What I'm talking about is not now making this a huge neural network that you do with gradient descent all at once, but actually having that inference mechanism inside the training where you try things rather than propagate derivatives, because I don't think that propagate derivatives can really solve everything. You do have to do test all possibilities.
Yeah.
You do. I mean, there's no free lunch.
No, and certainly not when it comes to memory access. So there's lots of talk about attention, and attention is a sort of way of looking up over parts of a representation or over different locations in a memory. But often that optimization will not be like a continuous thing, because the right place for the information might not be next to like the second most correct place, and so you probably can't find it like by descending. It might be that you need to explore. Yeah.
So learning memory access is hard because of the multiple ambiguity there, the way you mentioned.
I think it's hard because it's kind of a discontinuous thing. I mean, if you put some things in some memory, there's no reason why you ought to be able to find the right location without trying everything.
But that's only one of 20, right?
Yeah. So it works.
So
it works in this
right?
case.
It's not bad, right?
Yeah.
I mean, the space is small, right? So you can just try all.
Exactly, but in the general problem, if you want it to scale, I'm not sure you'll be able to train memory mechanisms to find information using gradient descent end to end. That might not be sustainable. Yeah, it's just an intuitive thing. Okay, some really quick point about human semantic cognition. So some of my work has involved trying to understand this a bit better. And there's a neuroscientist in Cambridge who did a really interesting piece of work where he looked at convolutional neural networks for image classification. And he actually compared them to 37 other ways of representing visual information, right? So of computing features from images. And many of these ways were ways which were popular in computer vision. And he compared them to brain activations at different parts of the visual cortex, different layers of the visual cortex, including up to IT, which is this part which is at the top of the visual cortex, which is supposedly a little bit more semantic. And he showed that the pre-trained convolutional network, so he's not really a deep learning expert, he just took a out-of-the-box pre-trained AlexNet, and he actually found that, oh, excuse me. Don't know what I did there. Sorry. He actually found that the ConvNet was the one that matched human brain activations most closely. He has a paradigm for comparing representations in different things. So he actually developed it for comparing representations in humans and monkeys because he wanted to see how similar they were for objects. But then he decided to compare humans, monkeys, and a convolutional network. So he found that they were the best match, which is a strange fact about neural networks and the human brain. I don't think it means much necessarily, but
were those activations computed and by probe or something?
No. So it was you put a person in a scanner and you show them an image, and it's fMRI signal. Yeah. So yeah, there are many ways to do that.
7 images. The correlation was high on 7 images, on a set of 7 or 8 images.
Right. Yeah.
Presumably, like the person has not gone through the whole ImageNet data set in the scanner.
No. So yeah, not the training sets, not even all 1,000 categories. I think it's about 256, a subset of 256. But then the analysis is based on pairwise similarities. So it is a lot of pairs, but it doesn't cover anywhere near the full sort of visual diet of. Anyway, so he was interested in me making this model a bit more semantic. Because what you get with ImageNet is these really like unnatural categories, right, as the targets. So not only are they weird concepts that we don't even know what they are, but also like lemon and then Rhodesian ridgeback, so different levels of specificity and things like that. And actually there's been some cool work in computer vision where people say, well, hang on a minute, let's make this a little bit more principled and see if we can get the model to perform better. So
Slide sorter, you might be able to advance. Get out of slide. Oh, you.
Oh yeah, I think I'm okay.
All right.
Yeah, thanks. Yeah. So what we did is we basically did that. So we tried to make these more semantically informed, and there's two ways. So one is we did a hierarchical softmax where the hierarchy corresponds to WordNet. So that's not particularly novel. I think people have been doing that a bit in computer vision. But we wanted to see, is the match with the human data improve? Another thing that we did was we put pre-trained word representations here. So rather than mapping different categories, atomic categories, to separate points that don't have any sort of semantic geometry on the space of categories, it's now the case that if the model maps to lion, it's nearby when it maps to tiger. So this is ongoing work, and we haven't ascertained whether or not this improves classification performance at test time. One thing it seems to do is improve errors, which makes sense. So you don't get these weird things you get with a trained ConvNet where it thinks that like a car is a tiger because the car has stripes. So probably car and tiger would be a long way away in our target space. So it's going to make an error which is more like what a human might make. That's the theory. One thing we have noticed is already that the mapping, the correlation with brain data is much better. So I should add a small disclaimer, which is that if you correlate word vectors with this data at the top level, it's already quite good. So the mere injection of the semantic orientation into this model seems to help. What's nice is that the mix is in some cases better than just the linguistic information. So one baseline is raw pixels at this end. Another baseline is the language-only vectors. And we've actually, at various points in the network, we get a better mapping with the brain data when you mix them. So it's a small pointer to how we can also try and bring together research in deep learning and language together with an understanding of how humans process concepts in order to improve performance in both areas. So really quickly, I've talked a little bit about the limitations. Something that fruit flies like, so if you go back to the dictionary model I talked about at the start, if you go back, something that fruit flies like, it's pretty good at that, actually. The RNN, I can do it now on the demo, but so this is a famously difficult sentence for, potentially for machines. It actually gets that one right. Okay, so it suggests melon, which is a nice thing. Something that time flies like, it doesn't do very well at that. Well, it could be just inventing its own metaphor here about hawk moths and time, but it probably just links them. Even more importantly, a habit that would annoy your boss, petulance. A habit that would not annoy your boss, boorishness. That's kind of like petulance. So basically, negation, the model is terrible when there's a really strong discontinuity between form and meaning. This is a problem for all continuous neural net models. So this is one area we need to improve. What can we do about it? So, I mean, there are many things. Lots of people will say, oh, just make sort of symbolic structures in the representation and continuous structures and get them to interact. And I think that may well be the case. I certainly believe that neural nets should be, in some sense, modular. I just think that that's probably even how the brain built stuff up with evolution. So I've got a feeling like there's going to be little subunits going on. Having said that, what I think is a nice, more fundamental thing to deal with it is by addressing the fact that life is not really like this. So here, in all of these models, and in a lot of machine learning, to be fair, we have a learning agent which observes the correspondence between inputs and outputs. This could be supervised or unsupervised learning, right? I mean, it's hard to make the distinction. In a language model, these things aren't labeled, but the model is still kind of thinking about what might be next, and then seeing what's next and updating. But in actual fact, when something learns, after a while, it can influence what it sees. So it can decide who it talks to in order to learn more about a certain thing. It can put it in itself in situations which change the inputs, which then it observes outputs, and then it learns from that, right?
This is like reinforcement learning, right? So output here will be the action, behavior, and
Yeah.
I change the word.
Exactly. Yeah. So you could think of it as the reinforcement learning problem, or here there's going to be some learning to learn in some sense, because after a while the model will have tried to learn certain things and failed, and then it will get better at knowing what it needs to do to learn stuff. So there's a kind of meta knowledge going on there. So I think, can we take the same models that I've been discussing, but make learning more interactive? So this is a kind of inspired by what Naboisha told me he's already done on Twitter. But you can imagine the same sorts of models that I've been describing, optimized to achieve an ongoing interaction with the user, and also to elicit output of a certain type, so retweets that exhibit a certain type of sentiment. So there's many interesting things if we can train an agent to do this, right? We can understand humans better because we can see, well, what sort of inputs, what sort of stimuli elicits positive responses from people. It's actually quite easy to elicit negative responses, but it would be much more, you probably have to be much more subtle to get positive responses from people. So we can learn about humans, but we can also learn about how the model understands. We can probe its internal representations, and we can find out which part of language it's focusing on and things like that. So that would be cool. We could also do things like, I've thought about a situation where you tweet something so that you establish who has a certain opinion, and then you try and train a model to change that person's mind. That would be pretty cool, right? So you can easily establish, like, hey, hands up, who likes Donald Trump or whatever. So then everyone comes in and has like a tweet about that. So you establish their opinion, and then maybe you can see what sort of rhetorical strategies there are for changing that person's opinion. There's a group on Reddit where basically the challenge is to change someone's mind. So it would be interesting to explore how models could learn to do that. Another way we could apply this same framework is generally learning to learn for language problems. So there's often this domain issue where if you train models on the language from a certain domain, it performs really well, but it breaks just a little bit away from that domain in a way that humans would never do. So maybe we can get models more human-like by having a selection model whose objective it is to decide at various points which text to train on. You then have the language model. Based on the output of the selection model, this model trains itself on a bit of text. And then it performs some task and evaluates. And based on the performance on that task, that gives a sort of reward signal, which can be used to update the corpus selection model. So this model needs to obviously be capable of representing a little bit of the language in the corpus in order to make a decision. So it can be a contextual model. But what would be nice is if this whole framework, a model could learn to plot its way through an environment of training data in a way which is more optimal than the obvious baseline, which would be just mixing it all up or training on everything. So this would be a way of modeling the way like a child maybe explores an area where it needs to learn more in order to work out how to ask for food in order to get food or something like that. So quick summary, I've tried to show that, at least in my work, I think we can do better by understanding human language learning and modeling computational language learning as a sort of joint optimization of two different problems. I've talked about the advantages of using distributed representations in language processing, how we can potentially add a greater context awareness to neural language models. I mentioned briefly how we can potentially also use these models to gain a bit of insight into how humans are solving the same problem. And then in the future, maybe sketched an approach in which we can combine all of this in more interactive learning environments to give us models and experiments which will tell us about human language learning and about computational language learning together. So overall, I'd like to know whether it can help us to achieve something like this. Really good performance of personal assistance, an output which is useful for people, And also maybe even a sense of how humans, like maybe not, it's not as simple an equation as this, but a sense of the information and the variables which humans use in order to satisfy the same problem. So that's the end. Sorry it went over a little bit, but these are all the people that I've worked with, and I'm really grateful for their help in doing stuff. So.